Let's review some of the rules of logarithms. So log base a of u equals x is a typical logarithm statement. The base value for the log is this number a here. This is a base, and it has to be greater than 0, and it cannot be equal to 1. The u value here is known as the argument. The argument of a logarithm has to be greater than 0. And then this x value here, we usually call the solution or the answer. Basically, it's what is this logarithm equal to. So again, if you have log base a of u equal to x, what that translates to is a to the x power equals u. And I like to remember this by drawing in an arrow like this. A to the x power equals u. So for example, if you were given log base 5 of 25 and asked what's its solution, what's it equal to, think about the arrow. 5 to what power? 5 to what power gives me 25. 5 to what power gives you 25? And of course, that is the second power. So log base 5 of 25 is 2. Next, we have the addition rule and the subtraction rule to review. In both cases, the logarithms must have the same base. Must have the same base. All right, so log base a of u plus log base a of v. We can combine these as one logarithm because they have the same base and because they have the same coefficient out in front. In this case, the coefficient is 1. So this combines to log base a of u times v. So an example using actual numbers, for instance, log base 3 of 7 plus log base 3 of 10, that would combine to log base 3 of 7 times 10, or 70. Similarly, with the subtraction rule, you can combine these two logs. They have the same base, which is a. They have the same coefficient, which in this case is 1, and we're subtracting. So we can combine them as one logarithm, but instead of using multiplication, the subtraction rule uses division. So we're going to have log base a of u over v. So another example, using actual numbers, log base 5 of 7 minus log base 5 of 12 gives us log, so same base, base 5, and since there's a subtraction there, we're going to combine the 7 and the 12 with division. There you go. The next rule comes in handy a lot in calculus. That's the power rule. And this power rule is fun to use, and people even try to use it on places where it doesn't apply, like trigonometry and like exponentials, like e to the power. Please don't do that. Power rule only works with logarithms. So for instance, we have log base a of u to the mth power. The power rule says that that power m can actually be brought down in front as a coefficient. So log base a of u to the mth is equivalent to m times log base a of u. Now, you might be wondering, why is that true? Well, here's an example as to why. If I had log base 2 of 7 cubed, right? That's the same thing as log base 2 of 7 times 7 times 7, right? 7 cubed, 7, 7, 7. Great. Hey, that's multiplication. I can use the addition rule to actually expand, take that product inside the log and expand it out with addition. There's 3 things being multiplied here together. So actually I can expand this to log base 2 of 7 plus another log base 2 of 7 plus another log base 2 of 7. So I use the power rule to expand it. Excuse me, I use the addition rule to expand it. Finally, how many log base 2 of 7s do I have? 1, 2, 3. So I have a grand total of 3 times log base 2 of 7. So again, that power up here comes down in front, boom, as a coefficient. So next up, we'll talk about converting bases. This is usually helpful when you maybe have a base that is, some random number like 7, and you need to convert your logarithm to base 10 so that you can use a calculator that you have handy maybe. So for instance, log base a of u, we can rewrite this as the ratio of 2 logs, And they can have any base whatsoever. So for instance, this could be log base b, whatever b is, of u, that one goes on top, and then log base b of a goes on the bottom. So b is, again, any base number that you want to pick. So b is any number. It could be any base number that you pick whatsoever. But remember, a base value has to be greater than 0, and it can't be equal to 1. And of course, it has to be the same base on top and bottom. So you see the argument goes with the base, the logarithm on top, and the base a goes with the logarithm on the bottom. So a quick example, log base 7 of 5, for instance. If I want to write this with make up any base you want, how about 14? So I can rewrite this as log base 14 of 5 over log base 14 of 7. Remember, the 5 goes on top, the 7 goes on bottom. Is log base 14 useful? Probably not, but that's just showing you that that's one way you can rewrite that log. What might be more useful is to rewrite it as log base 10, because maybe you have an old calculator and the only log that you can punch in is base 10. Okay, in that case, that would be log base 10 of 5 over log base 10 of 7. Doesn't matter, you can use any base value in the world as long as it matches the requirements for a base value. It has to be positive, can't be 1. All right, common log. If there's no base value shown at all, we assume that the base is 10. So for instance, this one here, I could have written this as just log 5 over log 10, log 5 over log 7, leave the 10s out altogether, it means exactly the same thing. So here, log 100, that implies log base 10 of 100. So 10 to what power gives me 100? 10 to the second power gives me 100. I'm just going to rewrite that here to remind us. Again, 10 to the second power gives us 100, and that's why log of 100 is 2. Another log that we use a lot is ln, natural log, and of course that base value is e. So ln of 52 equals x. What that really means is log base e of 52 equals x. What that really is asking you is e to what power gives you 52. And of course, you can use your calculator to punch in ln of 52 and figure out what power that actually is. Here's another one. ln of e to the 5th equals x. Remember, this means log base e of e to the 5th is equal to x. If you think about this logically, what that means is, if you use little arrows there, e to the x is equal to e to the 5th. Once you have it written like that, hopefully you see e to the x is e to the 5th. Well, clearly, x has to be equal to 5. That leads us to the idea of using inverses. So for instance, log base a of u is the inverse of a to the u. What do I mean by that? Well, what if I wrote log base 2 of 2 to the 10th power? Similar to the problem we had up here. The question is, 2 to what power gives me 2 to the 10th power? Well, hopefully you see that that's a 10, right? So 2 to the 10th power gives me 2 to the 10th power. If I cover this up again, think about this. The log base 2 is the inverse of the 2 to the 10th. So that basically the log base 2 and the 2 leaves me with 10, if you want to think about sort of canceling, which is not the right word here, but you get the idea. Okay. Another way we can use this, kind of the other direction, is 3 to some power. 3 to the log base 3 power, let's say, of 8. Well, a to the u power is the inverse of log base a of u. 3 to some power is the inverse of log base 3 of that same value. So the answer here, just a spoiler alert, the answer here is going to be 8. But why? What this says is, the logarithm says 3 to some power gives me 8. So this logarithm is representative of a number that 3 to that number gives you 8. And now I'm taking 3 to that power. So clearly that gives me 8. Right? Log base 3 of 8, let's say, equals m. So 3 to some power, 3 to the mth power gives me 8. So this is m. 3 to the mth power gives me 8. This whole thing is m. 3 to the nth power gives me 8. Likewise, ln of x is the inverse of e to the x. So ln, I'm going to write it though as log base e, just to make it really explicit here. Log base e of e to the x, again, e to what power gives me e to the x power? X. So some people think of this as sort of canceling. The log base e and the e sort of cancel each other out to give you the x. And again, I probably should have written this as ln, but I wanted you to remember the base there. So I could say ln of e to the x is equal to x. Same idea. E to the x power gives me e to the x power. Another way to think of this, kind of the other direction, is e to the ln power, and let's call it, I don't know, ln of 14. So I'm going to cover up the e for a second. What does ln of 14 represent? It represents the number such that e to that number gives me 14. So this power here represents a number. E to that number gives me 14. And guess what? I'm doing e to that number. So I should get 14. If that makes your head twist around a little bit, just remember if I have an e and an ln, they undo each other, and I'm left with 14. If I have an e and an ln, they undo each other, and here I'm left with x. Okay, a couple examples that have little complications to them just to remind you of what you can and can't do with logarithms and their inverses. So here I have ln of 4 times e squared. Well, a couple of things. ln and e are inverses, but ln and 4e are not inverses. So what I need to do is kind of get that 4 out of the way. How can I do that? Well, this is 4 times e to the second. So why don't we use the addition rule? I can separate this to ln of 4 plus ln of e to the second. Right? ln of 4 is just a number. There's not much more I can do with that. ln of e to the second, well, remember that power rule. That power on the e can come down in front as a coefficient. And ln of e is 1, right? E to what power gives me e? Just 1. So I have ln of 4 plus 2. Another way I could have thought of this is, oh, ln and e are inverses, so I'm left with 2, right? E to what power gives me e squared? The second power. Okay, e to the 5 ln x. Well, what does that mean? E and ln are inverses of each other, but I have to remember that e and 5 ln of x are not inverses of each other. So that 5 is in the way, kind of like the 4 was over here. Well, in this case, I've got 5 times an ln. I can use that power rule and rewrite this as e to the ln of x to the 5th, right? That 5 came up as a power on the x, on the argument of that logarithm. Now I know e and ln are inverses of each other, and I'm left with x to the 5th. Or you can kind of go through the whole logic of this power represents the number such that e to that power gives me x to the 5th, and now I'm taking e to that power, so I get x to the 5th. Last example here, I have e to the ln of x plus x cubed power, right? Since I have addition in the exponent, I need to remember that that means I have e, make that an e, to the ln of x times e to the x cubed, right? I've got addition in the power, and I can separate the bases like that. So now I have e to the ln of x. Well, e and ln are inverses of each other, so I'm left with x times e to the x cubed power. So just a quick reminder there about addition in an exponent, kind of a sidebar here. Remember, if you had, I don't know, 3 squared times 3 to the 5th, that's 3 times 3, and this is 3 times 3 times 3 times 3 times 3. That's 3 to the 7th. And really, what did we do? We added the powers. So just a little side example there to remind you. So if you have addition in the powers, you can separate that into multiplication with the same base. So e to the ln of x times e to the x cubed. Thanks for listening. Good job getting review on your logarithms.